Ragazzi, this is no website. What?
We can definitely tell time.
No, I can't.
Hello, hello, everybody. Thank you for joining us in this slightly warm evening. Welcome to Space Draft 108. My name is Lily Whitler. I am a PhD student at Steward Observatory, and we are happy to welcome you here to Space Drafts. For those of you who are new here, we are part of an international network called Astronomy on Tap, which is where astronomers from all around the world have these public talks in pubs and bars to share our love of space with all of you. So here in Tucson, the format of the show will be that there are going to be 20 to 25-ish minute talks with a 20-minute intermission in between, where we invite you to go refill your drink, take a restroom break, things like that. Now we have merch over there on that table. Unfortunately, it is cash only, but we would love for you to come check it out, come chat with us. We love talking to all of you. I think I didn't actually confirm this with you, and I should have. I think there will be a trivia question in this first talk. If not, there hopefully Mathieu will have one. When the trivia question comes up, if you want to raise your hand, try and answer it. If you got it right, if you choose to get it right, and you so desire, you're welcome to come choose a piece of merch from our table for free. As most of you, I think, here know already, because you're veterans of Space Drafts, we are right next to this active train line. Inevitably, there will be at least one train that comes through, tries to make it completely impossible to use speakers. So while we wait the train out, what do we all do here at Space Drafts? If you have a drink in hand, press the train and say choo choo, and then wait awkwardly for the next 30 seconds until the train until you get the new speaker again. What is here too? We can also choo choo the bus if we would like. Yes, the wheels go round and round. So I think that is all that I have on the introduction front. So without further ado, I'm going to let our research professor, Dr. Jianwei Lyu, talk to us about supermassive black holes.
Okay, I think I cannot see the screen, so I'd rather stay here. So hello everybody. It's a nice evening, and I'm an assistant research professor at Steward Observatory, University of Arizona. I'm also a member of James Webb Space Telescope science team. So today I will give people some brief introduction or just some nice features about supermassive black holes. So the talk title is Mystery and Marvels in Supermassive Black Holes. So uh, let's get started. Before we dive into any supermassive black hole directly, let's first take a look at the imaging of night sky. So this is some photo actually I've taken in the summer some years ago in Tucson. So when you look at night sky, you will see a lot of stars. And I think almost everyone knows, I'm not sure I can't see the projector, but anyway, I'm just pointing with my finger. So this is the Milky Way. So it's a region where there is a lot of stars, and there are some dust grain or dust filaments in it. So why I need to introduce that? Because first, we always want to know what's our location in the universe. A long time ago, people think, okay, maybe Milky Way is the whole universe. So what we can do is to count the number of stars in each direction and make a map of those stars. So actually, this is okay, sorry. I'm touching English. So actually, this is what been done by William Herschel. This is a very famous British astronomer who lived between the 16th to the 17th century. So this is a map we have got. And there is a small star here, black dot. And we conclude that's the location of our sun. Okay. So I believe maybe you have heard that actually our sun is not in the center of the Milky Way. So this is people who can typically find such pictures in some telescope, in those telescope. So actually, our sun is located in some spiral arms and distant to the Milky Way center. This dense bright region is about 8 kiloparsec. That basically corresponds to 26,000 light years. So basically takes light to travel like 26,000 years to arrive us. So it's pretty far away from the center of the galaxy. You may wonder why we have a different conclusion. Okay, people can have a guess, but I will give you an answer. That's simply because when we look at the Milky Way center, we see this dark region. This dark region is actually not empty. It's just because there are so many dust rings around line of sight block our field of view. Our line of sight, okay. And dust is actually almost everywhere in the universe. So this is a very famous constellation called Orion, and near the belt of Orion constellation, these are stars, there is a very famous nebula called the Horsehead Nebula. So you can say there is a dark region, just look at a Horsehead. People got the name. So this is imaging taken in the optical band. So you can see the Horse Nebula, this part is totally dark, okay, compared to the background. But if you take a picture at a longer wavelength, just basically the energy is lower, so you take a picture in the infrared band, you get an imaging like this. So the interesting change is the dark region right now becomes bright, okay, while the bright, like the purple like clouds become darker, okay. I can give people an explanation simply because the dust actually obscures the light in the background, and due to something called energy balance, when something observes some energy, it has to re-emit at longer wavelength. That's why we see the bright regions here. Okay, so basically the dust can show emission in the infrared wavelength. Well, the background nebula emission is just some gas emission. Gas itself does not show strong emission in the infrared. Okay. That's why we can see dust directly. Okay. And then we take imaging about the Milky Way center at different wavelengths. You will also see the change. So in the optical band, it's dark near the galactic plane, so along this direction. And in the near infrared, from 1 micron to 1.5 micron, you will see some orange-like region. Okay, but still you will see some obscuration effect, okay, because the dust is not totally transparent at this wavelength. And you move even to longer wavelengths, the mid-infrared wavelengths. So basically, you will say only the dust emission, there is no background. So to locate our Milky Way center or see the Milky Way center, we have to go to the infrared wavelengths, okay. And then people began to use some super big telescope with 10-meter apertures in size and take the Milky Way center. Now we named it as Sagittarian A. In different years, when you look at it carefully, the pointing of the telescope on the sky is exactly the same. So you will say the stars are moving, okay? And what we can do is just to plot all the stars as a function of time, and you can make an animation like this. So basically, if you look at the orbit, it seems that all the stars are rotating to some point, okay? So that's what we named as a Sagittarian A. And based on the speed of the motion as well as orbit, we can conclude that is a supermassive black hole. Okay. So we see the cartoon in the center of the Milky Way. There is supermassive black hole with the mass about 20 billion solar masses. So basically, the black hole mass is larger than the sun by 20 billion times. Okay, it's pretty massive. And then I can introduce why James Webb is important for this research. Okay. So before that, I will first introduce why we need to go to infrared, or what is infrared light? Okay, some background. So it's again the same scientist, astronomer William Herschel discovered the infrared light. So basically, people have used some prism to disperse the light from the sun into different colors. So it's like a rainbow color. And this person actually put a temperature uh, measurement here in the region that's in the longer side of the red light. Okay, although you do not see the light directly, somehow the temperature increases. Okay, that's he concluded that's something called infrared. That's out the right part of the spectrum. And here is what we can got from the most modern detectors. So this is a person with the arm covered by a black plastic. And if you use the infrared detector, you can completely see through the plastic bag. Okay, that's basically you have the power to see through the obscuration materials if you look at the infrared window. And actually, on the ground, it's hard to conduct infrared observation just because there is something called atmosphere. So this is large amount of oxygen and hydrogen, which will have strong emission in the infrared. So basically, it's hard to see the faint infrared signal from the universe. But then you have to put the telescope in space, like the James Webb Space Telescope. And I think most people may have heard this telescope. This is actually the largest space telescope ever put into space. It has a aperture diameter over 6 meters, and it's orbiting very far away from the Earth. It's something called the Magellan 2 point. So this is further from even further compared to the Moon. And it's an infrared telescope, as I mentioned, because we want to see something, see the universe behind the dust. Okay, so it has an operating wavelength from 0.6 to 28 micron. It's not only good for the study of obscure system, it's also important to study very distant universe, just because all the light in the distant universe will shift it to the longer wavelength. We will have to do an infrared observation. Yeah, it actually observe not only the distant universe, it also observe system in our Milky Way. It's a general purpose telescope. And here I just show some pictures of how people can put a telescope into space. Basically, you need to build one and put them into a rocket and unfold it. And if you work, it's way more complicated in real life, but the basic first step. So back to the black hole, I can briefly show people there are basically two groups. One called something called fluorescent black holes. Basically, there are some isolated black holes that do not interact with the surrounding materials. Basically, the black hole itself does not show light emission. But as you may have seen in the movie Interstellar, there is very beautiful black hole images. Okay, and it's bright around it. It's just because the light behind the black hole can be banned by the gravitational force of the black hole. Okay. It's not the black hole itself is emitting. Also, people may have heard something called Event Horizon Telescope. This is a direct imaging of the supermassive black hole in a not far away galaxy called M87. So this is actually the shadows of black holes and the light coming from the sources behind it. And another type supermassive black hole is called active black holes. Basically, in this system, it is interacting with surrounding materials by creating gas and dust. So basically, we never seen that directly, but based on all kinds of observation, indirectly, we can confirm there is something called an accretion disk. So basically, the gas and disk is forming a disk, and it's rotating pretty fast. And some materials will just pour into the supermassive black hole, but some other material will just emit the energy or the light and energy all kinds of light from the UV to the infrared wavelength. And depending how bright this accretion disk or this active black hole is, we can classify them into two types. One called active galactic nuclear. So basically, you can still see the host galaxies. Okay, there is a relatively bright nuclear that's called the active galactic nuclear. That is another major type is called quasars. In that case, the central black hole or the active black hole, active nuclear region is so bright it outshines the host galaxy signal. So typically you will say that's like a star, what we call the quasar stellar object. Okay. So that's the terminology. And people have begun to study the property of supermassive black holes as well as the property of their host galaxies, and finding this very intriguing relation. So when you plot the mass on the y-axis, the mass of supermassive black holes on the y-axis, and the mass of the central body, basically that's the central part of the galaxy, okay, people find a tight correlation between these two quantities. Actually, this is one of the tightest uh, correlation in the actual galactic astronomy, and people have studied this both from observation simulations, and there are a lot of speculations why there is such a correlation. And I want to mention why this correlation seems interesting or important is basically because the black hole and the galaxy have a completely different physical scale. For example, here I just show you the size. Actually, this is not the size of black hole because black hole itself is a point source. Okay, it's a size given for the this called something square of the influence. Basically, that's the distance that the gravitational force can influence the light. Okay, so we bend the light. That's the size of typical black hole. That's just that number. Okay. Then the active supermassive black hole AGN has a physical size around 1 to 10 parsec. Okay, you don't need to worry about the relative size. And the galaxies itself have a size from 10 to 100 kiloparsec. These are just some numbers. People do not have some direct impression on how different the sizes is. I will give you an answer. So the black hole, uh, the first sphere of influence of the black hole, I would say this is called Schwarz radius. Okay, that's the term. So you can compare that with the with the small ants with that side. And the agent and the structure in this block described as large as the Steward Observatory, the whole building. And the whole galaxy is comparable to the city of the size of the city of Tucson. So right now, people claiming that okay, there is a correlation between a small ant and a big city. Okay, it just have a tight correlation over several order of magnitude. That's actually unexpected discovery. Okay. Then people began to wonder why there is that. When people look at the galaxies, they say that galaxies can merge. Okay, this is just different imaging of different galaxies, and you will say that it seems like two galaxies can come together. There is some interaction showing this sedimentary or gas like a spiral structure, and later they can merge. Okay, like this. And the people then do did some simulation using some supercomputers, and this is the work from paper like 20 years ago. So basically, they argue that once you have two gases interact, come too close to each other, they will disturb. There's something called interstellar medium, basically destroy the standard galaxy structure. And there are a lot of gravitational influence, and there is a lot of gravitational field that the materials from the galaxies can pour into the center of each galaxy. And because there are so much gas and dust, the central region can have some supermassive black holes. In the beginning, it's obscured by dust, and later on, there is strong feedback. That basically some energy coming out from the creating supermassive black hole. It will remove the surrounding gas and dust, so that we will end up with a very turbulated galaxy. And this is a simulation for the star component. It's just the same idea, just showing the different part of the galaxy. We can just watch it. So because stars are just individual points in this simulation, so you actually do not say a lot like outflowing gas structure. Okay, but you will say how the structure of these two merger systems can be changed with different time. Okay. Yeah, basically it's just two gases merge together, then their nuclear will merge together. And some people argue that the central black holes in these two systems can be also merged. That's one way to build up the mass of the supermassive black hole. Yeah, so that's the end of the galaxy, and this is another simulation. It's a same simulation, but looking at different viewing angles. This is from the theta point of view, and this one is from the age-on point of view. Okay, I think we can skip that. That's the same kind of thing. This is the image. Okay. Then James Webb Space Telescope, we have used it to do a lot of follow-up study for not only nearby objects, but some high redshift quasars. And this is some imaging of bright quasar. People can use that to get some constraint on the stellar mass. And also people have taken some spectrum of the quasar. Based on how broad this line is, people can measure the sizes of supermassive black holes. Then we can have a lot of these points and plot them into these plots. And this green line here is what we have measured in the local universe, it's just like this. And the James Webb high redshift quasar observation showing the objects are distributed here. Okay, that basically tells you that the black hole mass, when compared to the whole galaxy mass, is way more massive compared to the low redshift universe. And this is another plot. The y-axis is the mass ratio between the supermassive black hole and the whole galaxy. And the x-axis just describes how young the universe is. Basically, this side is the nearby universe, and this is the distant or early universe. You will see this mass ratio have some kind of evolution at longer or like distant universe. There are more massive supermassive black holes. Okay, people have been studying why there is a relation, but it's complicated. And there are also a lot of aging or operating supermassive black holes are heavily obscured, like this. This is the cartoon. And at high redshift universe, people have found a large population of type 1 agent, basically some agent showing this broad emission lines. And look at their imaging is like a red dot. Okay, it's simply because they are too far away and the gas itself is very compact. Well, the agent is pretty bright. That's why we see this red dot-like object. And also using some medium-fried data points, and people can identify the obscured agent or obscured accreting supermassive black hole by looking at their spectral energy distribution. That's basically how the energy along the y-axis change with the wavelength. And here I just show you some images. I think the resolution is too poor, but I would point out that previously people have looking at this obscured agent mainly in the X-ray wavelength. And right now using James Webb, we can find way more obscured systems compared to the X-ray population. Okay. And also people have found some interesting nebulous structures along in distant agents. For example, on the left-hand side, the green-like color is the gas emission, and on the right side is just some RGE plots just with the stellar composition. We will find that there are some greenish extended structure in many of these obscure systems. Okay. And actually, I want to mention that we actually know this kind of object previously. So this is something called okay. I forgot the exact name, but it's some object people previously have been found on ground during the Sloan Digital Survey, and this is the HST, the Hubble Space Telescope imaging. So there is this kind of gas emitting structures outside the galaxies. That basically tells you that there are some gas in the host galaxies have been pushed away by the supermassive black holes. Basically, it's interacting with the host system. Yeah, then back to the, I want to briefly mention what's the most distant agent we have doing so far. And this is actually a galaxy called Jianwei 11. It's a distant object at a redshift about 10.6. That corresponds to like 400 million years. That's about 3% of the universe age. So basically, if you think the current universe is 100 years ago, 100 years old, and this galaxy have aged about 3 years. Why people think it's a black hole is because people have taken some spectrum of this object. And they say this kind of initialized. Okay, this kind of is initialized, and the only most people believe they can be expanded by some galactic nuclear or agent. So I think that's all I want to show. And I think the take-home message is just the supermassive black holes are super cool, and they can shape the galaxy evolution. And the second point is there is a lot of gas in the universe, and gas can obscure these supermassive black holes. And we need to go to the infrared using space telescope at James Webb. And lastly, is just James Webb is very powerful and have made a lot of wonderful discoveries. Yes, that's all. And so I just start with two questions. Yeah, I don't know the question, but I will just ask. I think I will just make an open-ended question, okay? But do people think that the number of galaxies, or how do you compare the number of galaxies and to the number of supermassive galaxies? You can make a guess. Are they comparable or some number is higher than the other? Can you give some explanation why you think that? Yes, that's a great answer. Okay, yeah. So this gentleman said that he thinks that there are way more gases compared to supermassive black holes. The reason is because there are some other systems like star clusters they do not have supermassive black holes. Any else? Okay. Yeah, I think that's a good answer. Actually, I can tell you that I also agree that there are more galaxies compared to uh, compared to uh, supermassive black holes. It's simply because for very low mass galaxies, because the black hole, even if it has a black hole at the center, because we have shown there is a tight correlation between these two points, the black hole in the center cannot be called supermassive black hole.
I was actually going to ask a question, but you're also welcome to clap. Yeah, I just wanted to, you presented some interesting, surprising things that have been discovered about black holes in the distant universe. Things like the black hole mass stellar mass relation kind of breaking down, how the CGMD11 exists. What have you personally found the most interesting and the most surprising?
Yeah, okay. I would say the most surprising finding is that in the past, people don't appreciate the role of active supermassive black hole in the universe. People normally think, okay, because the galaxies are so low mass, so we do not expect their aging in the center is active. But right now, I feel that my personal speculation is that over half of the galaxy population should have an active supermassive black hole in the universe. So in other words, once we observe a galaxy at some distance away, the redshift above 8 or whatever, they should have a agent. Why we don't say the agent is just because the agent is obscure.
Are there any other questions for Jianwei? Perfect time, this train. Going once, going twice. Well, let's thank Jianwei again for that wonderful talk. So it is now 8:04. Let's call it 8:05. So we will now be going on our 20-minute intermission. So we'll see you back here at 8:25. Feel free to come talk to us at our merch table. we're happy to chat with you. I'm sorry again that we can only take cash. So refill your drink, take a restroom break, make sure to tip your bartender, and please say thank you to Borderlands for having hosted us so generously up until now. We'll see in the future. But yeah, please say thank you to Borderlands. Hello, and welcome back from intermission. So we have no news tonight, so instead we are just going to get going with our second talk of the evening from I can talk. From Professor Mathieu Renzo from Steward Observatory, who will be telling us about massive binary stars once we find his slides. Cool. Thank you. Take it away, Mathieu.
Thank you. Thank you for sticking around and giving me a chance to talk about what I spend most of my days thinking about, which is the explosive life of massive stellar binaries. And I'll try to explain all these words in much more detail. But we're going to move down in scale from the scale that Jianwei was talking about earlier to the scale of stars and stellar systems. And in my research, I study massive stars. What do I mean by that? Massive stars are born with 7 times the mass of the sun or more, roughly. And these things are extremely rare. Less than 0.4% of all stars are this massive. But despite the fact that they're rare, they exist. This is a real infrared image of Zeta Ophiuchi, the nearest O-type star to Earth. And on top of being existing, so somebody should understand them. These are interesting to me because they end their evolution in gigantic explosions called supernovae that can outshine briefly an entire galaxy and mark the formation of a neutron star or a black hole, the most extreme compact objects that we have in the universe. And these black holes are much smaller than the black holes you heard about in the previous talks. But to understand their properties, we need to understand their progenitor stars and how they evolve. Even if you don't care about gigantic explosions and compact objects, massive stars are still extremely important for virtually all subfields of astrophysics. And that's because together with the supermassive black holes that you heard about in the previous talk, massive stars drive the evolution of galaxies. In particular, they're big, so they're extremely bright and hot. So their light can break atoms. This is called reionization and can influence the space most nearby to a star. But early in the universe, these kind of processes might have played a role at the cosmological scale. Massive stars are also extremely messy. They have constant outflows of material, which we call stellar winds, that can steer and shake the gas in the galaxy. And when they explode at the end of their life, they can swipe away the gas and shut off the formation of new stars. So massive stars regulate the formation of other stars in the galaxy. And last but not least, by my own definition, these massive stars are going to be burning through all the possible nuclear fuels all the way to iron. A star sustains itself by fusing hydrogen into helium in its core. That's what the sun is doing right now. Then once it runs out of hydrogen, the core will be only helium. This will proceed into burning helium into carbon, carbon into oxygen, and then the sun will stop. But massive stars will continue all the way to the point of their explosion. And all the materials that they produce as they consume fuels in their core will be returned to the galaxy. So, for example, all the oxygen that you're breathing right now has been forged in the core of a massive star. Now, I don't only study one massive star, I study 2 of them together in so-called interacting binary systems. So these are systems where you have 2 stars orbiting each other so close that they can exchange mass. And these mass exchanges will change both of the stars, how they look, how they evolve, therefore how they give their stellar feedback to the galaxy, and whether they explode or not and what comes out of the explosion. And the reason why I complicate my life taking 2 stars instead of 1 is because this is a very common situation in the universe. And sometimes this is presented as a new result. And actually, we've known about binary stars for a very long time. I assume that most people here are going to be familiar with the Big Dipper, which is a group of 7 stars that you can use to find the north. You take the last 2 stars at the bottom, prolong in their direction for 5 times the amount of their distance. Somewhere here, there's the North Star. Most people know this. What you may not know is that this was also used as an astronomy test to see if your eyesight was good enough to be an astronomy student in ancient Greece. And the test was find which one of those seven stars is a binary. And now here you have too many things on the way to actually test this. But as you walk home, you can see if your eyesight is perfect, you should be able to find the binary star in here. And I'm just going to give you the answer. It's this one. It's actually a visual binary, two stars called Mizar and Alcor. And Alcor comes from the Arabic, means the hard one to see. Today, we have telescopes, we can zoom in much more, and actually we know that Mizar is a binary of binaries. So it's four stars configured and as two binaries orbiting each other. And Alcor, there are claims in the literature that it might be a triple star. So there may be up to seven stars in a source that most of us with glasses would see as 1 point. This is, of course, just an anecdote, although historically relevant. Let's look at this a little bit more quantitatively. And this is a figure from a very comprehensive study that shows you as a function of the mass of the star on the x-axis, what is the probability that it has at least one companion with the with the bold symbols on the y-axis, and the probability that it has two or more companions, so that it's a triple, quadruple, quintuplet system in the thinner symbols. And as you can see, for the massive stars above 8 or so solar masses, 90% are in binaries, and like 50 to 60% are in triple stars. So having companions, being in a binary is extremely common. This, of course, doesn't tell you what the companion is. Maybe it's just a little pebble orbiting very far away from the star that cannot do much to it. But if you think about especially these very bright stars, they're massive stars that are shining in your face. It's very hard to see anything next to them unless it's also a pretty sizable, big and bright thing. And in fact, if we look at the young population of massive stars in our own galaxy, we see that about 50 to 70% of them are so close to a companion that we expect that at some point in their life, as stars evolve, they get bigger, and this will trigger a mass transfer phase between the two stars. One very last reason why binaries are important is that often they're the only way that we have to study black holes of stellar mass. So this is a different category of the previous black holes. The black hole is, by definition, something you cannot see. Light cannot escape it. But you can detect it if you have a star orbiting around the black hole and moving. And this is the same technique that we use to find exoplanets around stars. We can sometimes find something much bigger, although invisible. Sometimes there can be a mass transfer phase, not between two stars, but between a star and a black hole. And the material that falls into the black hole will spiral down like water in the drain. And although we cannot see the black hole, we can see this disk of material spiraling down. And last but not least, we have now been detecting in the past 10 years gravitational waves. This is a signal that is not light, we don't really see it, but it's the shaking of space-time produced when two black holes merge with each other. So it's again a binary system. And so what do I do with these kind of systems with massive stars in binaries? Well, I am a computational theorist. So the things that I would like to know are what are the physical processes that shape the evolution of these stars and that happen in their interior? And also, I would like to reconstruct the history of the life of these stars, where they come from and where they're going. But these are things that we cannot directly observe. Of a star, we only see the light coming out of the outskirts, like the peel of an orange. We cannot study the interior, only the peel. And so the way I do this is we think about the physics that we think plays a role here and write down equations that we then plug in a computer or a supercomputer to solve these equations and create synthetic models of a star. And this gives us access to the interior, but also allows us to speed up the evolution and go backward in time to see the past. But these models are quite complex. the physics that matters in a star is a lot of it, from atomic physics, nuclear physics, hydrodynamics, radiative transfer, and so on. So these models have a lot of moving parts, and to make sure we don't start making models that have no resemblance with reality anymore, we really need to harvest and compare with a lot of different observations. And here I want to highlight different categories of observations. We need nearby systems like Z of Yuki, nearest massive star to Earth, to have precise physical constraint. But precise physical constraint can also come from large populations of stars. When each star is observed in less detail, but you have many more of them to build up constraints. And then there are extreme events, such as the explosion of a star or the merger of a gravitational wave, that can give us some very indirect constraint on the life of stars, but allow us to probe parts of the universe that are too far for us to see the stars directly. And so here I want to now focus on what is the most common massive binary evolution path. When you have two stars, each with its mass, you can put them at different orbital separation. The orbits may be eccentric, so there's a large space of possible outcomes. And I'm going to follow here, focus here on the most common one. And this is, let's see if it plays. This is an artist impression movie that is informed by numerical simulations. You have two stars. The biggest one, the white one, evolves faster, swells up, and starts transferring mass. And what you see here is the ongoing mass transfer, which in stellar evolution terms is extremely fast. It might last 100 million years, 100,000 years, but this is for stars very short and very hard to catch on the spot. But the important thing is that it's going to be changing both stars. And I'm going to explain in a second in more detail how. And then the donor star, the one that gave mass away, explodes. This is the artist's impression of the supernova. And because of this explosion, the binary breaks apart. The other star is shot out and then continues its life traveling through space. And so this mass transfer phase is, of course, the thing that is most important to me. This is really what makes a binary different than just two stars. By having this interaction where mass flows from your right to your left, we are creating stellar structures that would be impossible if these stars would be living alone. And in particular, the donor star here on the right is going to lose all of its outer layers and remain as a bare, naked core made primarily of helium. And this star will then, because of this loss of mass, go from being the most massive one to being the least massive in the system. The other star that accretes the mass will be spun up by this material. That's because as you blow on a star, it's very easy to make it rotate, because all the mass of a star is close to the center, very deep, and the envelope is relatively fluffy. This material that comes in may also pollute the surface of the accretor star, especially if this material has been processed by nuclear physics processes somewhere inside the donor star. And finally, this change in mass, this increase in mass of the accretor star, can also refuel the star and make it live longer. And all these things are going to last much longer than the mass transfer phase itself. It's very hard to catch the stars while this is happening, but we can try to infer that it happened by looking at the consequences of this mass transfer phase. And then the second moment that was particularly important in that animation that I showed you is, of course, the supernova explosion. In that movie, that breaks the binary system. And this is something that we predict is extremely common. 60 to 90% of all binaries will break when the first supernova occurs. And this is mostly due to the fact that during the explosion, there are complex processes that are still under investigation that redistribute the energy between the ejecta being thrown away and the compact object, the neutron star or black hole in the middle. This is what we call supernova natal kick. And because of this kick, the compact object leaves the system and the system breaks apart. And we know that this happened because we can see neutron stars zooming around the galaxy. This is a real example of the optical image of the Guitar Nebula, where you can see at the tip here, there is one neutron star traveling at thousands of kilometers per second. You can think miles per second, you'll get the right idea. And this is much, much faster than their parent massive stars. And so something needs to happen, this supernova kick, when the neutron stars are born. But importantly, the kick only kicks the neutron star or the black hole. It does not kick the other star that is shot out exactly at the velocity that it had along its orbits at the moment of the explosion. It's shot like a slingshot, basically. And so this maybe allows us to find these stars that have been through binary interactions and then are ejected, looking at their velocities. So let's look at how fast these widowed stars can move. And the first thing is that they can be pretty fast. They can be runaway stars moving faster than 30 or 40 kilometers per second. But if you take a comprehensive view and look at the whole distribution, you can see that the vast majority of binaries break, but it shoots out not a runaway star, but a walkaway star that moves at maybe 10 kilometers per second. And this, unfortunately, is not a remarkable velocity in the galaxy. Most stars, this massive, move at about these speeds around the galaxy. So using just the velocity is not a good way to find them. And the reason why most are slow is because during the mass transfer phase, these stars grew in mass and the orbit widened. So for those that know Kepler's laws, these will decrease the orbital velocity of these stars during the mass transfer, and that's why they're shot out at slow velocities. And so if we want to find these widowed stars, we need to have models that tells us what to look for, because just the velocities is not going to be enough. But as I was saying earlier, these models have many uncertain ingredients. So how can we trust them? I'm going to argue that we can use the nearest O-type star to Earth to constrain these binary evolution models. And the reason why I started thinking that is because of this pink stuff that is on one side of the star. This is the analogous of a wave in front of a boat that is moving through the sea faster than the speed of the waves in the water. Then water piles up in front of the boat because it doesn't have time to get away from it. This is the same thing, but the supersonic version. Oops, sorry. So this is the stellar wind that is running in the interstellar material faster than the sound speed. And this suggests that the star is moving, from your point of view, to the left very fast. So maybe it was ejected from a binary. But the star is also very nearby, so we have lots of information on it. We know that it's fast. We also know that it's one of the fastest rotating stars that we know of. And again, this might be a product of previous binary interactions. And finally, it has a weird chemical composition. They're somewhat like the sun, but not quite like the sun. And we knew already that single star models cannot explain these properties, in particular the bold one here. And so the idea, if you're not convinced yet that this might be a binary product, we can also take the star and trace it back on the plane of the sky to its birth location. And we can trace back a neutron star, this red point, to the same point in the same cluster at the same time in the past. So the picture that is emerging here is that there was a binary system where mass transfer gave Z of Yuki, this star, its weird properties. And then there was an explosion that broke the binary and shot out the star in this direction and the neutron star in the other direction. And as a bonus fact, Earth, the solar system, used to be closer to this group of stars when this happened. And in particular, this very supernova may have contributed to a radioactive iron rain on the surface of Earth about 2 million years ago, which is something that we know needs to happen to explain the abundances of radioactive iron on the floor of the ocean. And so what we try to do is let's make a model of this star that accounts for the fact that maybe it was in a binary system. And we take parameters that are representative of the most common binary evolution. And then the idea is that after this mass transfer phase, the donor star is going to explode, and this will shut out the accretor star that will become our model for Zeta Fuki. And the question is, does this help explaining its properties? So let's go through the list again. And the first thing is the velocity. The velocity now is naturally explained because it comes from the fact that the binary broke, which is what happens in 60 to 90% of the cases. And getting it in the right ballpark with the constraints that we have is not particularly hard. Then the star is fast rotating. That's because during the mass transfer phase, the mass accretion spun it up. And this happens late in the evolution of the star, and it spins it up to the maximum possible rotation. And so we put in a lot of rotation late, we still get it when we see the star today. And last but not least, the surface chemical composition is weird because it's a mixture of the composition that the star had at its birth, which is kind of like the sun, plus some material that comes from the other star, the donor star that transferred it. And so out of the box, without fine-tuning our models, we can get better explanations for the properties of the nearest outside star to Earth and gain some confidence on this common evolutionary path for massive stars. And yeah, and what we're doing now with people in my group and collaborators is trying to explore a little bit more what this means for the interior structure of the star, how big its core is, what physics goes on there, and also working with observer colleagues and friends, trying to find more of the stars ejected from binaries at the first explosion. And even though I'm a theorist, about a couple of months ago, I did my first observations here in Tucson. And so now let me ask you one question. It's going to be very simple, but I also want to know the reasoning behind it. And so if you have these massive stars, they often come in these interacting binary systems. Which star will explode first and why? The less massive one explodes first. So at what point in the evolution? Okay, so the idea is that the least massive star after the mass transfer phase is the one that explodes first, which is the correct answer. This star, the star that starts as the biggest one here, donates mass during the mass transfer, and then it's not that it cannot hold on to its core, really, it's just that by the time it has given away most of its mass, what's left is already evolved. The clock is already ticking and there's no way to stop it. So indeed, the donor star, which at the time of the explosion is the least massive one, will be the first one to explode. And because it was the least massive, the other star is the slowest on its orbit. And if it gets shot out, in most cases, it's going to be slow rather than fast. And the idea is that because of this mass transfer phase, the properties of these stars are slightly different in subtle ways that we can recognize and that allow us to use the nearest stars to Earth to constrain the evolution of the most exotic sources of transit in the universe. And just as a final little bonus fact, what about the future of Zeta Fuki? So this star is now traveling through space, and there is really nothing that will stop it. It will continue to travel through space relatively fast. But at some point, as stars do, it will start growing in size, growing in volume, and become a red supergiant. So we expect that it will become a red supergiant runaway. We will not be around to see that when it happens, but we can look elsewhere in the night sky to find an example of a red supergiant runaway. And this is another very famous constellation that is visible in the winter, Orion, that was also shown in the previous talk. The shoulder of Orion is a very famous star, Betelgeuse, which also happens to be a runaway star. That this structure here, that's the same as that pink structure in front of Xanophyuki. It's because the star is moving so fast. And this star is also very nearby. It's the nearest old massive star to Earth. It's interesting that both the nearest massive stars are runaways, but it's also very puzzling because very recently people have proposed that this star is still today in a binary, despite the fact that it's moving fast as well. And this is a puzzle that right now I don't know the solution to. And that's all I wanted to tell you. Thank you. Are there any questions? Yeah. The question is, how long will it take Xanophyuki to become a red supergiant? Xanophyuki is about a 20 solar mass star. It's about 7 million years, so 3 more million years, give or take. Like millions of years, anyways. Is there another question out there? How do we probe the internal structure of the star? That's a complex question. There's different ways, each with their own shortcomings. The first thing is indirect probes. Like we have a pretty good understanding of the overall life story of a single star that is confirmed by many indirect observations, like how they sit in a cluster. Then there are more direct probes, like you can look at so-called astroseismology. So this is looking at earthquakes on stars, and these cause small fluctuations in their brightness, and the timing of these fluctuations in brightness tells you something about how waves propagate in these stars, which tell you something about the interior structure. Then there is other indirect probes like the nucleosynthesis. The fact that we understand why the universe is made of what it is made of requires understanding the interior of stars, and it's not a direct probe, but it's an indirect probe that we have a solid understanding. And there are many more aspects. If I think a little bit more, I'll come up with other examples, but it's an indirect game. Well, for the interior of neutron stars, that is actually harder to do, and therefore there are more mysteries in the interior of neutron stars. One way is through X-ray observations. The neutron star density is so strong that you can kind of see behind it. It will, like light that goes away from you, will be bent back towards somebody behind. And that tells you something about the mass distribution in the neutron star. Ideally, gravitational waves from the merger of two neutron stars could also tell you something about where they tidally disrupt, and so how if they're held together. But that is a much more difficult task. Thank you.
So much for the wonderful talk. I mean, thank you all for being here and for tolerating this slightly warm weather. We will be back on July 15th, the third Tuesday in July, as usual. Keep an eye on our social media. We will plan to be here at 7:30 p.m. that day. So keep an eye on our social media if anything changes. Otherwise, yeah, thank you all again. Feel free to come talk to us at our merch table, and otherwise, we will see you next month.